Hi, grade nines. We're back to a video lesson again. Sorry about this, but I was to the emergency room tonight. Apparently, I have pneumonia, so I'm going to be taking a couple of days off here, and hopefully, you don't have any real problem with the video that I'm leaving you. So this is actually the last lesson, and then tomorrow you'll do a review, and Monday you'll do a review, and then we're looking at probably having your next test next Tuesday. So we're looking at direct and partial relations today. So our goal is I know the difference between direct and partial linear relations and can work with either to solve problems. So we're looking at these two words, direct and partial linear relations, and sometimes we call them direct variation and partial variation. So we're going to take a look at how that looks in a graph and how that looks in a table of values. So starting with direct variation. A relationship shows direct variation if one quantity is just a multiple of the other. So if you can write an equation that says y equals 5x, and there's no plus or minus out after that, which means that there's no initial value, then that is called a direct variation. It is a direct multiplication of one quantity to another. So what does that look like? This means there's no initial value. This type of relation is always linear and will always contain a point 0, 0. So if we take a look, where can we see that point 0, 0? Well, it'll be down here on a graph, and it'll be here on a table of values. And so we're just going to actually put these dots on the table of values. 2 here is 40. 3, if I go up, is 60. And if I look at 6, oh, that was 4, not 3. Whoops. Well, let's get rid of that. 4 is 80. So that should be 80 there. 6 is 120. And then our graph kind of goes away. And so we're going to try and use the relationship to finish the next couple of things here. So remember, we can use the rate of change. So this is going up by 2 every time, and that's still going up by 2. So on this side, we're going up by 40 every time. So if we're going up by 40 every time, then this is going to be 160, and this will be 200. Okay. Now, we said that if it's a direct variation, that's going to have this 0, 0, and the y is going to be a direct multiple of the x. So that means I can find a number that multiplies x to give me y, and it has to work for every single part of this table. So what do I have to multiply 10 by to get 200? I hope you're saying we have to multiply it by 20. So this is times 20. Now let's double check the rest of them. 2 times 20 gives me 40. 4 times 20 gives me 80. 6 times 20 gives me 120. It looks like we're doing good. Okay. Now from the graph, pick 2 points on the graph and find the change in y and the change in x. So we're going to pick 2 points, doesn't matter which 2. And we're going to find the change in y. So I'm going to pick a different color here because the change in y is going from here to here. As I move from this point to this point, I move that far on that axis. And as I move from this point to this point, I move this far on that axis. So the change in y is 40 to 80, so that's 40. And the change in x is 2 to 4, so that's just 2. So that was rate of change from the graph. The rate of change equals the change in y divided by the change in x, which in this case, usually we shouldn't go all the way across, but I didn't leave you a whole lot of room here. So that's going to be 40 over 2, which equals 20. And what rate do we have here? The top is measured in kilometers, and the bottom is measured in hours. So the rate of change has a rate of kilometers per hour. Now from the table, remember our rate of change is what our x's go up by and what our y's go up by. So this is 40, and this is 2, and it happens all the way along, 2, 40, So determine what both the x's and y's go up by, and then it's the same thing, rate of change. Okay. In this relation, the blank quantity on the y-axis, so the distance, that's what's on the y-axis, the distance varies directly with the quantity on the x-axis, that is time. Time. The distance varies directly with time. They're going 20 kilometers every hour. Okay, so properties of direct variation. The first thing we want to know is that the graph goes through this point here. Do you remember what that's called? That is called the origin, which is also known as 0, 0. I don't care which way you put it, but the name of it is the origin. The y column is just a multiple of the x column. So that's what we found here. It was a multiple. We multiplied by 20. And you can get the y values by multiplying, oops, woo, multiplying, whoa, something weird's going on here. Multiplying the x values by the, well, where did we see this 20? We multiplied by 20, and if you look over here, it's the rate of change. So multiplying by the rate of change. Some of you may have recognized that just by the spacing that I left there. Okay, so that is a direct variation. Let's take a look at what's on the next page. Pause this if you need to. Hopefully everybody's able to stay caught up. There wasn't a whole lot of writing there. Now, partial variation. A relationship shows partial variation if one quantity is not just a multiple of the other, but instead shows an initial value. The graph will still be linear, but it will not go through 0, 0. So instead, it passes through the y-axis at its initial value. So for partial variation, there is an initial value. That's the biggest thing. There is an initial value. Okay, we've got to figure out what to do here. So distance driven, we have to get from 0 to 100. Probably each one of these being 10 will work, but remember, I'm not going to label every single one. We're going to start at 0 here, and then 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. We could keep going if we wanted to. 110, 120. We don't have to go anymore. Okay. Now up the side, I have to get up to $55. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. So I've got 15 spaces to get up to $55. Let's see, would fives work? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. That might be a good idea. There's a little bit of space up there, but not much. And fives are easy to label. So I think we're going to go up by fives. So we're going to go 5, 10. I'm just going to write the 10. 15, 20. 25, 30. 35, 40. 45, 50. 55, 60. And now let's put these ones on here. We don't know what these ones are. Okay. We don't need to know what they are. We might be able to find out where they are on here. And we don't have to put every single one of these on. I'm only going to put on the ones that are nice. So we went up by fives every time. This one is definitely nice. 155. So we're going to go 100. I'm going to follow the 100 up. There's 50. 100 all the way up to 55. I'm going to follow that over to make sure, yep, it's at 55. So there's that one that's nice. And is there another nice one? 80 and 52 isn't too bad. 60 and 49. Let's try 60 and 49. We'll keep them nice and far apart so that we can draw our line a little bit better. So 60 and 49. So 60 and I'm going to go up almost to the 50. So there's the 50. This is 55. I got to split this into like 5 spots, so it's just under the 50 right there. Now, am I going to join this with a solid line or a dotted line? Do you think they charge per all these fractions of a kilometer along there? Probably not. They might charge you for half a kilometer, but they're probably not going to charge you for a tenth. They're going to round it up, which means that not all the information is good in between there, but some of it is, which means we need a dotted line. So I'm going to take this and get a dotted line, and I'm going to try to draw a good line on here. So there, there. Let's try to get it to go right through there. Make this a nice, there we go. Now we could fill in the rest of this if we wanted to. What is the rate of change? Can we go backwards from here? What's it going up by every time? To get from 49 to 50, it goes $1.50. So that's $1.50. And then this is another $1.50 and another $1.50. So we can follow this back if we want to. So let's actually do that. So let's follow the pattern back, because these are going back 10 every time. So every time we go up 10, we go up $1.50. So when I go backwards, when I go down 10, I have to go down $1.50. So 49 down $1 would be 48, down $1.50 would be 47.50. Then if I go down $1, I have 46.50, and that's going to give me 46. Then the next one, if I go down $1, it'll be 45, and then another 50 cents is 44.50. If I go down $1, I'll have 43.50, but then I have to go down 50 cents, so it's just 43. And if I go down $1, it gets me to 42, but then I have to go down another 50 cents, so it's 41.50. And if I go down $1.50 again, it gives me right to 40. That didn't look like it goes through 40, and it really should go through 40, unless I made a mistake. No, I just double checked my numbers, and it doesn't look like I made a mistake there, so probably why it's not going through 40 is because we're off on that dot, because that dot wasn't a very nice one to graph when I had to graph 49. So let's just fix this and make it go through 40. And then this will come down and go right through that point, and you'll see it's kind of just a little bit below. So it's not too bad. We're off there. Okay, so here we go. Now for this one, the total cost, the initial value, that's not in the right spot. That should be over on your fixed cost. The fixed cost is your initial value, and the cost of driving is your rate of change. So for this one, we have to figure out the rate of change and the initial value. We just figured out the initial value. Initial value is 40. So the initial value is 40. And the rate of change is what the y goes up by over what the x goes up by. And in this case, we were going up by 10 every time. And over here, we were going up by $1.50 every time. So this is $1.50 divided by 10, which is 0.15 dollars, which is 15 cents, and that is per kilometer. So if we want to write this equation for car sharing, the total cost equals the fixed cost, which is 40, plus the cost of driving, 0.15, times the number of kilometers driven. I don't care what we put in there, n. You guys like using an n yesterday, so we will use an n. Any questions about this? Write them down and ask me when you see me in class again. Okay. So this is partial variation. And partial variation differs from direct variation like this. The previous example shows partial variation. The cost doesn't vary directly with the number of books ordered because we have a fixed cost that is constant no matter how many books are ordered. Books are ordered. Okay, that wasn't books ordered. That was car driving. Okay. The cost doesn't vary directly with the number of kilometers because we have a fixed cost that is constant no matter how many kilometers are driven. Okay, so the properties of partial variation. It has a constant rate of change. So it is a straight line, still has a constant rate of change. It's still a straight line, which means it's linear. Constant. All right, constant rate of change. It has an blank value, initial value. It has an initial, okay, this is really starting to bug me here. Initial value. It doesn't start at the, what is 0, 0 called? Origin. Origin. The graph starts on the, we're going to call that, it starts on the y-axis or the vertical axis. On the vertical or y-axis at the fixed value, and we call this the y-intercept. The rate of change, same as always, is the change in y over the change in x. So comparing direct and partial variation. For a graph, direct variation goes through the origin, goes through origin. Partial variation does not go through the origin, does not go through the origin. Okay. On the graph is for both of these, it is a line, a straight line. It doesn't curve. It is a line. For the equation, there is no initial value. So the equation is going to look like C equals 10n. And over here, for a partial variation, there is an initial value. There is an initial value. So that might look like C equals 10n plus 3. And the relationship for both of them is linear. 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 Has a constant rate of change. Constant ROC. Constant ROC. Okay. All right, what do we got next? So example number 1. If you are given a situation, how do you know whether it represents a direct or partial variation? Which of the following are direct and which are partial? How do you make a decision? Okay, let's take a look. A plumber charges $60 for a consultation fee and $30 an hour for the work they do at your home. Okay, the first giveaway here is that there's two numbers given. This is an initial value, and this is a rate of change. And if there's 2 given, we've got an initial value. It is not direct variation. It is partial variation. Next one. It costs $15 every time you take your dog for a flea treatment at the vet's. There's only one number here. What is that? Is that an initial value or a rate of change? Since it's happening every time, it's happening repeatedly, it's going to need a variable with it. So this is a rate of change, and there isn't an upfront cost. There's no initial value. So this is a direct variation. A salesperson at the Gap is paid $60 per shift plus 20% of every dollar she sells. Okay, now this is a weird way to write it, but this is a rate of change. She gets a certain percentage of what she sells, so that's a rate of change. And then this is what she gets. She's coming into work, she gets $60 no matter what. It's an initial value. So this has both, so it's partial. Now this should be pretty straightforward. Got to take a look. Okay, this one, initial value, rate of change. That is partial. This one here, is that an initial value or a rate of change? It's got a variable with it. Since it has a variable with it, it must be a rate of change. And there isn't another number, there isn't an initial value, so this must be direct variation. And for this one here, we've got a number by itself, and we've got a number with a variable. That's our initial value. Oops, sorry. That is our rate of change. Rate of change, and this is our initial value. Okay, so if it's got both, it's partial. So make sure that you get that clear. Direct only has one thing with a variable, and partial has your initial value and your rate of change. Now, how about for these ones? Do they have an initial value and a rate of change? Okay, remember direct variation has to go through the origin. So in this case, this is the origin on each of these graphs. Only direct variation goes through the origin. So which one is the only one that is going to be direct variation? I hope you're looking at this one. That's the only one that's direct variation. It's the only one where the spot that I circled has the line going through it. The rest of them are partial. Okay. Next example. Each month, Alex's cell phone plan costs $15 plus 10 cents per minute of use. Okay, write an equation for Alex's plan. I'm hoping this is getting easy for you now. So we have the cost. He pays $15 no matter how much he uses his phone, and then he has to pay 10 cents per every minute he uses it. So you can put in N for the number of minutes, or you can put in M for, excuse me, for the number of minutes. I'm going to pause this for a second. But there's our equation. Is this direct or partial variation? Well, you got to keep them straight. This is an initial value. If you see an initial value, that means it's partial. Which graph could represent Alex's total monthly cost? Okay, so let's take a look. It has to be $15 to start with. So this one we can eliminate because that goes through 0, 0. It's a direct variation, so it's not working. This one is going to go, if I continue on, it's going to cross underneath 0. So that's not 15. So this one doesn't work. This one, that looks like it could be 15, but it's just straight across. So it has an initial value. It doesn't have a rate of change. It's not changing at all. So that doesn't work. Hopefully it's this one. Okay, that looks like it could be 15, and then it's going up for the minutes, and that's what this is saying. $15 plus going up for the minutes. So this one could represent it. So example number 3. Identical pennies are placed in a container and the total mass is recorded. Complete the table and graph. And write an equation for the relationship. Is this direct or partial variation? Identical pennies. Let's see, we got to get from 0 to 10. This has time on the bottom. This is not what we want. Time on the bottom is not. This is number of pennies. So pennies. And mass up the side. And the mass is going to be in grams. So we need to get to 10 along the bottom. Do I have 10 spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I do. So I'm just going to go 2, 4, 6, 8, 10. I'm not going to label them all. And now up the side, I need to get to 75. So can I do it by 5s again? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75. That's probably good. So I'm going to go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, and that's as high as we need to go. So let's take a look here. I can put on 4 and 60. So we go 4 and all the way up to 60. And then I can do 6 and 65. So 6 up to 65. And then I can do 10 and 75. And we could, I'm just going to switch colors here. If this is an identical penny, we know this is going to be a straight line. So if I go up 1 and over 2 to get to that point, then I need to go up 1 and over 2 to get to another point. And if I follow that pattern backwards, I can go back 2 and down 1, back 2 and down 1, back 2 and down 1, back 2 and down 1. There, I've got a line there. I don't even have to do any math. I can just follow that pattern, and now I can pick those points off the graph. 0 down here is at 50. Let's put that on there. That's kind of cool. 2 was at 55. And 8 was at 70. So we didn't have to do any math. We can just follow the pattern on our graph. Okay. Write an equation for this relationship. Now we do need to know rate of change. So this is going up by 2, and this is going up by 5. So the rate of change equals the change in y over the change in x. It's going to be 5 over 2, which is 2.5. And our initial value is 50. Now I am going to put a line on here because there is some useful information between the points because there's 1 penny that we've left off there. But I'm going to need to make it a dotted line because it's just the 1 penny that's in between there. Not everything is going to be a good line. Whoa, that's not what I wanted to do. Undo. Let's take the line, that one. Oh, I need that. There we go. That's what I was doing. Okay, here we go. So we'll go, whoops. We'll go from there. Oh, no, did it again. How many times do I need to do this? This is a comedy of errors here. There we go. Got it. Okay. There's our dotted line going through those points. There. So we put that on there. Now, write an equation for the relationship. So what have we got here? This is mass. Whoop. Let's make that a solid line again. So this is mass, and this is number of pennies, so we'll call it P. So for mass will equal, start with 50 plus 2.5 pennies. Okay, if these are identical pennies, why is there an initial value? Anybody have any idea? Identical pennies are placed in a container and the total mass is recorded. So what do you think that initial value is? Any idea? Take a look up here. Identical pennies are placed in a container and the total mass is recorded. It must be the weight of the container, right? So the initial value is the weight of the container and then 2.5 grams for every penny. Yeah, that sounds about right. Okay, so is this direct or partial? It's got initial value, so it's partial. Use your equation to determine the number of pennies present when a total mass is 185 grams. Okay, so here's our equation. M equals 50 plus 2.5 P. Now, it has said the total mass is 185. Now, is that 185 an M, or is it a P? Is it a mass, or is it the number of pennies? I hope you're all yelling out that it's a mass because it's in grams. So we have to put it in for the M. And we're going to solve for the number of pennies because that's what it says. Determine the number of pennies. So it's asking us for P and it gave us M. 50 plus 2.5 P. So now let's solve it. We're going to have to use our algebra methods from the last unit. So we're going to subtract 50 on both sides. And that's going to give us 135 on this side equals 2.5p. And then we're going to divide both sides by 2.5. And that gives us 135 divided by 2.5 is 54. So 54 equals p. So therefore, there are 54 pennies. Yeah. I think that is it, right? Yep, that is it. Okay, so that completes this unit. So you have some homework to work on, and I will hopefully be back. I don't know how long I may be off, but good luck.